Hello, everyone. So we are now on Unit 2. So we're starting our second unit now, which is probability using counting principles, permutations, and combinations. So the name is a little longer. I hope that doesn't intimidate you too much. It's really just covering three lessons, and they're all kind of related to counting. So you will not believe it when I say it the first time, but counting is actually a very difficult thing to do. It's actually quite complex, more complex than we think. So what we're going to learn about in this unit is just about different counting techniques so that we can more efficiently measure the probability of bigger events, more complex events. So in the first unit, we were basically still looking at quite easy events for the most part, except when we got maybe to conditional probability, that got a little confusing for some of you. But I think now that we get to counting principles, it is going to get a little bit more complex, just because there's new techniques that you probably haven't heard of. But I'm hoping that you can use your own intuition, your own experience to kind of help you with this. So the first thing we're going to focus on today is counting principles. So what we're going to look at is how to use counting principles to count the total number of outcomes. Then we're going to distinguish between independent and dependent events. And then the last thing we're going to look at is how to use the multiplicative principle to find probability of independent events. And again, don't worry about writing the learning objective. I write that for you so that you're aware of what we're covering, but you don't have to write it in your notes. It's totally up to you. So as I mentioned already, counting definitely is not something that's easy. I think that every time I start this unit, people think it's crazy. Like you think, if all we're learning is how to count, this is going to be an easy unit. It's not that simple. Sometimes it is easy, like you think. Sometimes it's more complex. So for example, let's look at a real life example that might be really quite hard to do if you really think about it. So you have a lock that has five different slots, and then each slot has 26 letters to pick from. So how many different passwords are possible? Now, keep in mind when we talk about passwords, the order does actually matter, right? So, for example, I could have A, B, oops, and for some reason the eraser came up there, A, B, C, D, E. Or I could have, as another example here, I could have A, C, D, E, and then just for fun, maybe there's a G there randomly. And the order does actually matter. So I could have all these here and I could switch around the order. I could switch them around backwards and forward. You're gonna be there all day if you are thinking of all the different combinations of five letters that you can think of. It is not an easy task, and trust me, you do not want to be writing that out. I know that we did that for the first couple of compound events that we looked at. So when we were looking at rolling two dice or flipping three coins, we actually wrote out all the possibilities. I do not suggest that in this case because you have five different letters, and then on top of each letter, you have 26 different outcomes that you can pick for each one. That's going to be a very time-consuming task. So what we want to know is there a faster way to do this? And that's what we're going to learn about in this lesson here. So the first key and really important tool is using a tree diagram. There's also an outcome table. We don't talk about it as much. I'm going to focus just on the tree diagram. I figure it's better just to focus on one tool and really get good at that. So how do we use tree diagrams? So tree diagrams are basically illustrations of compound experiments, and compound experiments are experiments that happen back to back, right? So maybe we are as an example, we're tossing a coin which has heads or tails, and then on top of that, we decide to spin a spinner. So we do two things at once. So we do the coin first, and then we spin, or we do a coin plus the dice here. And again, this is my 3D dice. That's just a little illustration here, and I have no idea which one actually goes next to the one, but I think it's something like that. So it's again just a little picture there. Here's so you could have a coin with a dice or a dice with your spinner. You could have a spinner with the cards, whatever you can think of. So that's a compound experiment. So it's basically experiments. It's a sequence of smaller experiments that you have. So again, some of the quick examples: rolling two dice, tossing three coins. So we talked a little bit about this before. The only difference now is that we're going to try to see if there's a faster way to write out all the outcomes, and more importantly, a faster way to count all the total number of outcomes without doing all the work. So the first tool here is the tree diagram. And what this does is it's a visual illustration that basically lists off all the combinations that are possible. The outcome table is very similar, and I'll show you what it looks like. But to be honest with you, I'm going to focus more on the tree diagram in this lesson. So let's look at an example here. So let's say that you're tossing 3 coins in a row and you want to make a tree diagram to draw all the possible outcomes. You actually might recall that we did this example earlier in the last unit. So I think most of you already know the answer. There's 8 possible outcomes, but I feel like we found that answer by writing it out step by step. And again, it was relatively easy because we saw it several times. But let's say you had this for the very first time. How would you do this? Well, what I would recommend is a tree diagram. So first I'm going to have heads and tails written off like this, and hopefully I have enough space there. And what I'm going to do is for both of these outcomes, I'm just going to write over top the coin that I'm flipping. So this is coin 1. So in coin 1, I have 2 choices, heads or tails. For coin 2, I have 2 other options for each one of these outcomes. So if I have heads, in the first try, I can have heads again, so heads, heads, or I could have heads followed by tails. For the tails, if I got tails in the first coin, I could have heads followed right after the tail, or tails followed by another tail. And then my last option here, I go to coin 3, and in coin 3, I'm going to continue this on. I'm going to say, well, from this last outcome that I had, which was heads followed by heads, I can have another branch falling off here, and that leads to another head. So I could have heads, 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 or I could have heads followed by the head right after it, and then that would be directly followed by a tail. So far I have heads, 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 tails. Next, I go to my next branch here, which is the tail right after the heads. And I notice that I have 2 separate branches that come from it, right? So after each branch, what I notice is that I have 2 more options, right? So I keep expanding each branch, branches out into 2 more options, right? Heads or tails each time. So this last branch that I had that went from heads to tails, I can have heads, tails followed by heads, or I can have heads, tails followed by another tail. And I did run out of space a little bit, but I'll try my best to squeeze it on here. Then for the heads, the tail followed by the heads, I could have the tail followed by the heads, followed by heads, or I could have the tail followed by heads, followed by a tail. And finally, I have the tail, tail, and from this last branch here, I have 2 more branches that come from it. So I could have the tail, tail followed by the heads, and then I could also have the tail, tail followed by the tail. So what this does is it visually shows me all the different outcomes. So normally what we do once we have the tree diagram, we actually like to put it all together and simply write out what the outcomes are. So we try to write it down a little bit more neatly. So let's go through them step by step here. And let me just find a highlighter here. It's probably going to be a little bit easier to track. So the first one I have heads, heads, heads. And so that's going to be my first outcome here. So I'm going to write down heads, heads, heads. And then for the next one, I'm going to write down heads, heads, tails. And so I write down heads, heads, tails. And sorry for switching the color there. And then for the next one, I have heads, tails, heads. And so I write this down here, heads, tails, heads. And the next one is heads, tails, tails. So heads, tails, tails. And I continue on. So I have tails, heads, heads. So I simply follow each branch to find out what the outcome is. And tails, heads, tails. And the next one I have tails, tails, heads. And I apologize, I know it's a little slow. And the last one is tail, tail, tail. So there are all the 8 outcomes there. So that's how we do a tree diagram. And again, some of you might have seen this from before. And I know that we definitely started talking a little bit about the tree diagram. I just didn't fully go into detail of it, but now you've seen it all. So this is actually what the tree diagram would look like altogether. So this is kind of showing you how each branch then branches off into two separate parts, two outcomes, right? Heads and tails. And so in the end, we can see here that we have a total of 1, 2, 3, 4, 5, 6, 7, 8 outcomes. So you might start to notice a little bit of a pattern. The only hint I'll give you right now, I won't say it right away. Notice that this has two outcomes for the first coin. Obviously, when we toss the second coin, we have still two outcomes. And then of course, for the last one, we still have two different outcomes. And notice that the total is 8. Maybe you'll start to notice a bit of a pattern. Let's look at another example here. So let's say that you're picking out an outfit and you have to pick between a green, blue, or red shirt. So you have three choices for shirts: a black or brown pants, and then finally you have to pick between a white or tan jacket. Not gonna lie, the sequence of these colors I thought were kind of weird. I don't know, but who knows? I'm no expert in this, but I just thought it was a bit weird. So what we'll do in this case is we will simply think about all the different combinations that we have. So in the first one here, I'm maybe going to write down shirt. So this makes sense. I'm just going to try to organize it. I'm going to write down shirts, and right over here, I'm going to write down pants. And over here, I'm going to write down jacket, and I'll try my best to organize this nicely. I might run out of space, but I'll do my best to keep it all together. So for the shirt, I'm not actually going to draw the shirt. I can maybe draw one shirt for you. I know you guys appreciate my little drawings. They suck, but I try. Here are the pants. That's supposed to be pants. And the jacket, I'm not even going to try. I think it's like a longer jacket. I don't know, something like that. I'm not sure what the difference is between the shirt and the jacket, but you can, the jacket is slightly longer. And it has a weird sleeve there, but anyways, we ignore that. So what we're going to do in this case is we're going to make it a little bit easier. We're going to subcategorize this. We're going to say green, blue, red. And I hope you don't mind, I'm just going to keep one color just to make it a little bit easier. So I have three choices for the shirts: green, blue, or I have red. And then what I'm going to do is I'm going to think about all the combinations that could come from wearing the green shirt. Well, if I decide to wear the green shirt, I then have two choices to pick for the pants, right? My two choices for the pants would be the black, and I'm going to say BL and BR. So BL or BR. And then for the jacket here, just make sure I'm using different letters here, W and T. So what I do next is I then think about, okay, well, if I ended up picking the green shirt and the black and then the black pants from the green shirt with the black pants, I still have two choices still to make about the jacket. I can still pick the white or the tan. And of course, if I pick the green shirt, then the brown pants instead, I still have the two choices for the jacket, the white and the tan. So there's still more and more choices, even after you picked it already, right? So after I pick the green shirt, and this is just picking the green shirt, I still have to pick between the two pants. And then once I pick the pants, the black or the brown, I still have two more choices to make there for the jacket, white or tan. So that's for green. So that one's all done. So now let's look at the next one. We have blue. So if I chose a blue shirt, same idea as before, I can choose a blue shirt with black pants, or I could choose a blue shirt with brown pants. And then from that, I can still make two more choices for the coat. And I apologize, I'm really running out of space here. White or tan. And same with this one, I have white or tan. And let's go to the last one here. So if I picked a red shirt, I have the red shirt followed by, and you know what, I do not like that one. I think I'm not gonna have space. Let me just erase it. Okay, so we go back here. So if I pick the red one, I could have the red followed by black, or I could have the red followed by a brown, brown pants. And then once I pick the red shirt with the black pants, I still have the two choices for the jacket, just like before: white or tan. And I'm running out of space here, I apologize. And then for the last one, I have white, and I'm so sorry, I ran out of space, or tan. So what we're going to do now is we're just going to count all the different combinations that we have. And it might be easier if we just kind of say them out loud, because I do feel like it got a little messy in this question. So let's read them out loud together. So we have the green shirt followed by the black pants with the white jacket, not bad. Or the green shirt, the black pants followed by a tan jacket. So that's 2 so far. Then we have the green shirt followed by brown pants, and then we wear it with a white jacket, or the green shirt, the brown pants, and the tan jacket. So altogether, we have 4 up here, just so we're keeping track of the numbers. Now let's keep going. So if I picked the blue shirt, I would have the blue shirt, which could be worn with the black pants and the white jacket, or the blue shirt with the black pants and the tan jacket. And I could also have the blue shirt with the brown pants, and then I wear the white jacket, or I have the blue shirt, the brown pants, and then the tan jacket. So in this little group right here, just so I'm keeping track, this right here is my next 4 outcomes that I have. And now let's look at the very last one here. So I have my red shirt with the black pants and the white shirt. Whoa, and I don't know why I erased that. Apologize. So for some reason, this switches into an eraser every now and then. Yes, okay. So followed by the white shirt. So I'm just gonna put that back on here. As you can see, I'm going really rogue here. So we have the red pants, the red shirt, black pants, white jacket, red shirt, black pants, tan jacket, red shirt, brown pants, white jacket, red shirt, brown pants, tan jacket. So that the very bottom there is definitely a smaller number. I'm just gonna keep track of this one. This will be the last 4 here. Will be 4 outcomes. So how many outcomes do we have altogether? Well, we have 4 for each color at the very beginning. So that's going to be a total of 12. Again, hopefully you might start to notice a bit of a pattern. So I'll give you a little hint here. For the shirt, we had 2 possible outcomes. So remember, we had 2 outcomes for this one, and I'm going to switch the color back so you can see it a little bit better. So we had, 3 outcomes. I don't know why I said 2 outcomes. 2 outcomes for the shirt. We had 3 outcomes for the shirt, 2 outcomes for the pants. And sorry, I erased that by accident. 2 outcomes for the pants, and then of course 2 outcomes for the jacket. So let's piece it all together. So I have 3 outcomes here, 2 outcomes here, and 2 outcomes at the very end. Do we notice anything, any pattern here? Well, one thing you might notice when we branch it out, what we're really doing is we are expanding out our options, and really what we're doing is multiplying. So you might already be familiar with this. So for each of these outcomes for the shirts at the very beginning, we multiply it by 2 because we have 2 choices for the pants. And then of course we multiply it by 2 again because we have 2 choices for the jacket. But then so that means we have 4 choices for each shirt, but we have 3 shirts at the very beginning. So that's a total of 12. So what we kind of notice here is that really all we're doing to find the total number of outcomes is simply multiplying each of the outcomes that we can have in each experiment. So in the first experiment, which is choosing a shirt, you have 3 outcomes. For the next one, you have 2. For the next one, you have 2. And what we notice is that if you multiply the three numbers of outcomes that we can have in each experiment, we get the total number of outcomes. So we're going to actually write this out formally. So this is the counting principles here. So what's the shortcut to finding the total number of ways to perform 2 or more experiments at the same time? Well, we kind of noticed that if you multiply the number of outcomes at each step, you will get the total number of outcomes. And this is basically the fundamental counting principle. And again, I would definitely write this one down just so you remember what it is. It's essentially saying that if there are m ways to do something, so let's say that you have 1 experiment here, and there are m ways to do it, right? And then you have another experiment that you do right after, and there are n ways to do it, and n and m just represent some number of ways to do it that we don't know yet. All we're saying here is that if you want to find the total number of ways, just multiply them together and you will get the total number of ways. So it's going to be m times n. And putting this all together, how does this relate to what we talked about in terms of outcomes? Well, what we know is that if we have two experiments and we have experiment A and then we have experiment B, if there are NA number of outcomes, so again, count the number of outcomes in experiment A, and there are NB number of outcomes, so counting the number of outcomes in experiment B, the total number of outcomes will simply be the number of outcomes in A times the number of outcomes in B. This is all it's saying. So count the number of outcomes in A, count the number of outcomes in B, and multiply them together. And this works when we have two consecutive events. So in other words, again, repeating this again, so make sure it's clear. If you want to find the total number of outcomes, you multiply the number of outcomes at each step. So let's look at an example here now that we know the shortcut. So in the original question, it said that we have 5 slots and then there's 26 choices or 26 letters for each slot. How many different passwords can you create? And then as follow-up to this question, how many different passwords can you create if the first letter must begin with an A? So let's go step by step. So if we have 5 different choices, 5 different slots here, and then every single one of these slots has 26 different outcomes, then according to this rule, all we should be doing is simply multiplying the number of outcomes at every single step. So for the first letter, you have 26 choices, the second letter, 26 choices, the third one, 26 choices, the fourth, 26 choices, and the fifth one, 26 choices. So if we multiply them all together, this will give us the total number of passwords that you can create. And you can totally leave 26 to the power of 5, that's fine. Or if you actually want to calculate what that number is, feel free to grab a calculator and figure out what that is. So 26 to the power of 5, and I'm quickly grabbing my calculator here. I don't have it with me. 26 to the power of 5 would be 11,881,376. So a lot of different outcomes, okay? And so for the next one here, for the next part, it says, how many different passwords can you create if the first letter must begin with an A? So this is just a little bit of a change to the question. So if the first letter there has to be an A, it changes your answer around a little bit. So because it's actually going to be an A in this case, you don't have 26 choices. You actually only have one choice because we already picked out what the first one has to be. The first one can only be A, right? Because we just said that. We said that it has to have an A at the beginning. So it's going to be one choice for the first one, but the other ones have still 26 choices. So the only difference in this in the second part is that we're going to have 26 times 26 times 26 times 26 times 1, right? So instead of having 26 multiplied by itself 5 times, it's just multiplied by itself 4 times. So 26 to the power of 4, obviously times 1, because there's only one choice for the first letter there. And that's 26 to the power of 4. And again, if you're interested in what that number is, I can just tell you right now, 26 to the power of 4 ends up giving me 456,976. So our next part of the lesson is looking at independent versus dependent events. So I feel like we started discussing this a little bit, but now we're going to formalize this. So independent events are two events that occur simultaneously. So what I mean by simultaneously is back to back. They occur at the same time, basically. So like you toss 3 coins, you're going to do them back to back, right? So it's independent events are two events that occur simultaneously, but they have no effect on each other. So they don't actually affect each other at all. So an example, going back to rolling a dice and then tossing a coin. These are independent of each other because if I decide to roll a dice and then I toss the coin, it shouldn't have any sort of effect, right? Like if I get, as an example, let's say that I toss the coin and it lands on the 5. that shouldn't change the odds that I get a heads or a tails here. That shouldn't make heads or tails less or more likely. It's not like your coin has recognition and or has a memory and it's like, ooh, I should pick tails because I got a 5 or I got a 6 on the dice or on the die. It has no memory, right? So if these two events are completely independent of each other, they don't affect each other. Likewise, if you had two coins and you flip them, just because you got heads in the first one doesn't mean that your other coin is going to remember that and be like, oh, you got heads, so I'm going to get tails. There's no memory, right? It's just doing it randomly. It's chance. So these are completely independent of each other. Same with two dice. If you have two dice, just because you get a 6 on one doesn't mean that your other die is gonna say, oh, I should not get a 6 because the other one had a 6. No, it can just be any one of the 6 choices there. So that's what an independent event is. Another example is you drawing a card, and let's say that you pick a card from a deck of here. So let's say you have a deck of cards here, and you have 52 cards. You pick a deck, and you pick a king, and then I put it back in the deck. So if I put it back in the deck, it shouldn't change my odds at all. It's not like your card is, has, or you have a memory and you're going to say, okay, I'm going to, and again, this is assuming we pick randomly and it's well shuffled. Obviously not if it's not shuffled well. We assume that if you put the card back, the odds of picking any of the cards are equally likely, right? The outcomes should not change. The likelihood should not change at all. So as long as you put the card back, it shouldn't change the likelihood of picking another card. There should be no change. Dependent events, on the other hand, do affect each other. And we've actually talked about examples. We already gave examples of this. The perfect one is picking a card from a deck. And if you don't replace it, and we talked about this, if you don't replace the card, and let's say that I ask someone to pick a card, and then instead of returning it to the deck, they don't return it. That changes my odds of getting another card. How does it change it? Well, instead of having the probability out of a sample size of 52, it's now going to be out of 51 because I took out one of the cards. And also, if we are finding the odds of getting an ace and I already picked an ace, well, I already picked an ace. So it's actually going to be 3 out of 51. So that's an example of dependent events. So basically picking cards from a deck, but you don't replace them. That's the key part. Replacing or versus not replacing. If you replace them, then they are independent. If you don't replace them, then they are not. They are dependent. Hopefully that makes sense. So what do we know? Why are we talking about independent, dependent? Well, there's a reason for this. We know that dependent events, we actually talked about dependent events when we talked about conditional probability. So dependent events basically rely on each other, right? They actually will have an effect depending on, so if an event occurs before it, it will affect that current event's probability of occurring, right? So what we're saying in this case is that if two events are independent, then the probability that, let's say event B, I'm just making this up, event B is rolling a 7. So the probability of rolling a 7 given another outcome, and I don't know what that outcome could be, it could be anything there. If they are independent, two independent events, then we're basically saying the probability of B happening given that A happened is still going to be the probability of B happening. So we're essentially saying is that the event B does not rely on event A to happen to change its probability. The event B will still be the same probability no matter what because it doesn't rely on A. So that's essentially what we're saying here. The probability of B, given that A happened, if they are independent, then the probability of B given that A happened is just the probability of B. That's it. So hopefully that makes sense. And again, I should probably be clear here, and I forgot this, if events A and B, that's what I meant to write. I can definitely fix that in the slideshow there. So the multiplicative principle for independent events basically only works if the two events are independent. That's a really important thing. So this is only going to work if it's independent. So if it is independent, we have a bit of a shortcut. So I think you remember this from the conditional probability lesson. we talked about how the probability of the intersection of A and B is the probability of B given A multiplied by the probability of A happening. Well, we just learned something really important. We learned that the probability of B given A, if A and B are independent, is equal to the probability of B. So instead of writing probability of B given A, which is more confusing to write and more confusing to find, we can simply write the probability of B multiplied by the probability of A is the probability of the intersection happening. So in a nutshell, what we're saying is the probability of A and B occurring if they are independent is the probability of A times the probability of B. You simply multiply them. Hopefully that makes sense. Let's look at an example here. So we're flipping two coins and then, so we're flipping a coin and then we roll a die. So I'm just gonna draw this out here. So obviously we have heads or tails for the die here. And then for the dice, we have 6 different outcomes and I'm just gonna write them out. 1, 2, 3, 4, 5, and of course 6. So what is the probability of flipping heads and then rolling a 5 in a single trial? So doing this all at once. Well, for the coin toss, the probability of flipping a heads, we know that it's pretty easy. That's just a half, right? And again, because these events are independent, we can definitely use that shortcut that we learned. The shortcut basically says find the probability of heads. So find the probability of heads multiplied by the probability of rolling a 5. Rolling a 5. And this will give you the probability of having a heads followed by a 5. So what we're going to do is simply, and again, I just got lazy with this, instead of writing heads, I wrote H. So probability of having heads and a 5 will be the probability of having having heads multiplied by the probability of rolling a 5. So the probability of getting heads here is a half, and then the probability of rolling a 5 is 1 out of 6. So now all we need to do is simply multiply these two results and we are done. That means that the probability of getting heads in the coin toss and 5 in the die is 1 out of 12. That's it. So let's look at one last example here. Drawing cards with replacement. So really important word here. You're going to see a lot more of that as we go along, with and without replacement. So if you are replacing your card, this changes your odds a bit. So if let's say that you draw a first card, so the first card you draw it and then you put it back in the card. What is the probability of drawing a queen on the first draw? So the queen is going to come in the first one here, and then you're going to have an ace right after. So all we really need to do is multiply the two probabilities together. And again, why do we multiply them together? Well, we multiply them together, and it's a nice, easy shortcut because they are independent. If they are not independent, you can't use this shortcut. Okay, so just to be clear, this only works the shortcut of multiplying the probability of A times the probability of B. If we're finding the intersection of A and B, that only works if they are independent. If they are not independent, then we need to go back to our original formula, the multiplicative principle when for conditional probability. So we'd have to go back to using the probability of A and B, intersection A and B, is the probability of B given A multiplied by the probability of A. So it's a little different, right? So just note the difference. They're not exactly the same. But because this is independent, this is definitely the easy case. All we're going to need to do in this case is simply multiply the probability of getting queens, a queen on the first draw times the probability of getting an ace on the second draw. So we multiply the probability of getting a queens, which is 4 out of 52, times the probability of getting an ace, which is also 4 out of 52. And again, you might want to reduce this. So if you reduce this to 1 over 13 times 1 over 13, and then multiply through, that gives you 1 over 169. So that is the probability that you get a queen and an ace. Now, one small thing. This question specifically said that there was a queen in the first draw and an ace in the second draw. What if it said you can have a king or an ace in any order? that's a little different. So hopefully you kind of notice the difference there. If I have a queen and an ace in any order, then technically I only found out this sequence of events. I found king followed by ace. But what if I switch it around? What if this if set in any order? Well, I could do ace followed by queen. And luckily, the great thing about this is that it actually gives you the exact same probability. And I know it's the exact same probability because it's 4 over 52 times 4 over 52. So that means that the probability of the ace followed directly by the queen would be 1 over 169. And this right here is 1 over 169. So I'm just going to write this here. And so if I want to add up the two answers together, I have to consider the two cases. I add them up in this case. I end up finding that it is 2 out of 169. Again, don't stress too much about this. If you're kind of confused about that last part, we will definitely talk about this later. But this just giving you a little intro into the the kind of what do you call it? The complicated side of counting. That there's more to consider than just a formula, right? So make sure you read the question carefully because there are different parts to it. So that's basically it for now. This is the homework, and again, do your best to get through as many questions as you can, and please post questions on the discussion board, as a lot of you are already doing, which is great to see. And please make sure that you ask for help. Thank you.